Great. Well, thank you, Fadl. And thanks to all of you who are taking time during the conference to think about ocean IoT. And I'm going to share my screen and there.
We can see it.
Okay, great. So as we think about this, I wanted to sort of put it in the context of some of the things that oceanographers are being asked to do. And I couch these problems in the terms of prediction, because people don't want us to just understand the response of complex ocean ecosystems to climate change or understand ocean hazards. They want us to be able to predict them so that we can avoid harm, and so that we can avoid consequences. So predicting the response of complex ocean ecosystems to climate change. What does it mean for the plankton on which the whole ecosystem depends? What does it mean for fisheries? What does it mean for iconic environments like coral reefs? They want us to determine the whole biodiversity of the ocean, including its microbiome. And we figure that we probably know less than 5% of it now. They want us to be able to predict ocean-related hazards like harmful algal blooms and sea level rise, and manage ocean food resource systems, whether those are wild fisheries or the aquaculture that Fadl talked about. Predict the future of the polar oceans that are changing so quickly. So, like predicting weather, this is going to take really vast quantities of information, vast quantities of observations, as well as the ability to use that data well, and to have models for it. So we're nowhere near the persistent synoptic level of observation that is required for that. And so it's not just that we want to know as much about the surface of the seafloor as we know about Mars. It's that we live here, and we need to be able to do this in order to understand how to live sustainably on the planet. So one of our very famous oceanographers at Scripps, who just died a couple of years ago at 101, said that the 20th century was the century of undersampling the ocean. And we want to get away from that. We want to get to the point where we can sample both by measurement and other kinds of physical samples in a way that leads us to this predictability. So as we think about this ocean internet of things, we usually tend to focus on the things, and we certainly have a lot of things that we have made, sensors, instruments, platforms. They have tended to be done in sort of out of a legacy of design process that really goes back to the 1950s. And part of that is because of the challenge of operating instruments and sensors in the ocean. First, the ocean is saltwater, so you have to have something in a case to protect it. And if there's any leakage, your instrument stops. Second, the ocean, there are great pressures in the ocean. So there's essentially 1 atmosphere of pressure increase every 10 meters you go down in the ocean. So if we want to be able to explore this entire expanse, 70% of the surface area of the ocean, or a surface area of the planet is ocean. If we want to be able to explore that, we want to be able to explore all of it. And the pressures for something at 500 feet, 150 meters, are 15 atmospheres or 220 pounds per square inch. At the sort of an average depth of the ocean, 5,000 meters, the pressure is 500 atmospheres, and or about 7,300 psi. So that's why our instruments tend to be spheres, so that pressure isn't a problem, or torpedo shaped, things that have lots of appendages don't work so well. Third challenge that we have is that light doesn't penetrate very well. Even blue light, even shorter wavelengths of light have trouble penetrating water. And then seawater has lots of things in it to disperse and diffuse light. So you really can only use light as the electromagnetic spectrum over a very reduced distance. Sound, on the other hand, travels exceptionally well in the ocean, but of course the bandwidth is very low. And the last challenge is that anything that things in the ocean love substrates. And the minute you put something in the ocean, things start attaching themselves to it. So very quickly, if you have an optical window of any kind, it's encrusted with things. If you have mechanical parts, you have things growing on them and impeding it. So this has led oceanographers to have sort of a conservative approach toward the design of what the instrument is going to be in and how to do that. And I think that also has, it's been a damper on innovation and design. Nonetheless, we've done a lot, and I'm going to show you a couple of examples of what oceanographers consider to be networks. So most of our networks are really of individual types of gear that are sent out into the ocean or taken out into the ocean to sample it for its properties, like its temperature and salinity, or to take samples, and then are brought back with their data. And the integration is done ashore, and it's a very, very intensive and labor-intensive process. So it's a network only in the sense that it may be operated in a way that is planned for sampling to take place by different kinds of instruments in the same place, or it's integrated afterward. But it's not a network in the way that we think about networks of things on the internet on land. A second type of network that we use are a variety of cabled observatories. So in this style of network, a submarine communication cable carries power and carries the ability to communicate, and some kind of a central junction box or node in the upper left, that would be the orange device there, is connected by the cable to land, and then smaller cables connect other kinds of instruments. And probably the largest of those is two or three different arrays that are off the west coast of Oregon and Washington, and they're designed to be able to provide information about a seafloor spreading center to the west of that area, the Juan de Fuca Ridge. So the cables come from land, they go out to along the ocean bottom to some central node, and then there are other nodes of instruments over that. And in general, everything that's connected to it has to be connected by wire. So there aren't autonomous devices running around the ocean from these places. There are pilot projects now to be able to do that by setting up a mooring from this power source, having a node to which an autonomous device could come back to, dump the data, and be recharged. But these have been very, very difficult to design and execute. And it's not, there are individual experiments, but it's not a standard way of operating yet. Another example is autonomous networks of floats. And this is a figure showing that we have a network of almost 4,000 floats that work autonomously. And essentially what happens is that these are deployed from a ship. They sink rapidly to about 2,000 meters depth in the ocean. They float there for about 5 days, and then they come up rapidly. And when they come up, they measure temperature, salinity, and depth, and they send that data back to a central processing location. So over time, we have developed now an array of about 4,000 of these. We don't control the location of them. They float at depth in the ocean, and that in itself is a source of information because it tells us where the currents are moving at that depth. And this is called the Argo array. And what you see there in the picture on the upper right are Argo floats. So that is a network, and it has, for oceanographic comparison, it is a very dense network. So roughly 4,000 profiles every 5 days of the ocean is unheard of density of information for us. And over time, that's given us really incredible insights into what's happening in the ocean. And this is just one example of them. It's a time series of data. It's the average temperature with depth in the entire ocean. So this is not one location. It's integrated over the entire ocean from the surface to about 2,000 meters. And then from 2006, when there were enough of the floats deployed to really have fidelity, and until 2017. And during that time, the big result from this was that the entire upper portion of the ocean, the entire upper 2,000 meters, is warming with climate change. Not just the surface, but the entire volume is warming. And in fact, we know from these data that the ocean is taking up 93% of the heat generated as a result of greenhouse gases in the atmosphere. So it is really buffering us from far more intense impacts in the atmosphere and on land. And it's an example of what you can do when you really have a lot of data and you're able to look at that in very powerful ways. So those are some examples of things we've been able to do with current technology. So when I start this, I'm turning the sound off, you'll know exactly what it is. On February 18th of this year, I don't know about you, but I was riveted to my TV screen watching the Perseverance rover landing on Mars. And these amazing images are the actual photographs of that deployment. And we were seeing them with only the time delay of the time that it took that communication to get from Mars to the US. And we're able to actually experience this as though we were at NASA, or experience it as though we were on Mars. I'll just fast forward here to here as the instrument is actually using AI to select its own landing site from within the area that was selected for it. And then finally, at the very end, whoops, went a little bit too far. We were able to see the landing site, and then see the sky crane separate from the rover. I cannot tell you how envious oceanographers are of this level of communication and ability to experience something and see it happening. And I'm sure that, and obviously we can celebrate, yes. We can send instructions to the rover without being connected to it. We're telling it to do things. We're telling it to sample. We can't do that in the ocean unless we are directly connected by some kind of cable or device. And I think that's part of what we're thinking about for this Ocean Internet of Things. We made a major step forward in July of 2017 when NATO unveiled Janus, the first standardized acoustic protocol for undersea systems. Before this time, there was not even an agreement on the acoustic standards for communication between various instruments. And it took the navies of NATO wanting to have that and agreeing to amongst one another to form a protocol and then argue out what the protocol would be in order to realize this. In all the time that we've been putting instruments in the ocean as researchers, we haven't come up with an agreed upon protocol before. So another one of the obstacles that we face, coming to agreement on how to do things. So there are a lot of ideas now for how we might develop networks. And this is one example. It's an example from a couple of Scripps faculty members who are proposing that we develop an ability to get seismology data back from seismographs on the seafloor. And what they're proposing is that there would be autonomous floats that would be acoustic transmitters up to wave gliders on the surface. And a wave glider is a small platform about 10 feet long that's powered by wave action. And it is directable, so you can tell it which direction to go and keep it in the same area. So this is one idea about how we would control, how we would form the internet part of that Internet of Things. Using autonomous vehicles to be transmitters. And so here's a little graphic of what would happen. The seismometers would be collecting data. They would transmit it to an intermediate, and then that intermediate would send it up to a wave glider on the surface and communicate back to land. Another idea is to put acoustic sources in the ocean and essentially develop sensors that would be incorporated, that would be tuned to that acoustic frequency so that they could be controlled underwater from an acoustic sense. And again, you have very long range with such sources, but not a lot of bandwidth. Another idea is to put sensors into planned submarine cables going across the ocean, and then to use the power and bandwidth of communications cables to be able to um, collect data and send it back to land. And some of the cable companies have already agreed that if sensors could be developed that wouldn't interfere with or slow down the communication rate, that they would be willing to incorporate them into cables. The cost of laying such cables is not insubstantial. Thus, the idea of putting them where cable companies were already planning to put cables. This doesn't get us off the bottom of the ocean, but it is another idea for a network. So another great historic figure at Scripps, a previous director, Roger Revelle, said that great periods of oceanography are defined by new kinds of instrumentation. And I think of this not only in terms of the sensors and instruments that are the things, but also these networks. And those in themselves would be incredible instruments, because of course the ocean would affect the transmission of the acoustics. It would affect transmission from the cables, and that in itself would be another kind of ability to look at large scale things in the ocean and large scale changes in the ocean. So these kinds of things may of necessity be developed in a modular fashion and connected later. But if we want to be able to answer those really big questions about the biology of the ocean, about hazards in the ocean, we need to think at the scale of how we're going to be able to infuse the ocean with the level of sensor density that we experience on land. And I think that it's important for oceanographers to work with your community to establish the protocols for doing this, so that you're sensitive to the issues that we face as oceanographers with this very difficult medium, but also that we enable everybody with those protocols to start working much more rapidly and in ways that are compatible. So as we think about this, we also need to think about the data itself. And I was struck by this this quote on from the book "The Internet of Things: Evolution," or no, I'm sorry, it's not a book. It was a paper, "Evolution or Revolution," and the author said that how well an industry or individual company utilizes the mass influx of data unleashed by the Internet of Things objects will greatly determine its competitive advantage and future success. And I think that that's pretty much the same for us. How well oceanography utilizes the influx of data unleashed by ocean IoT objects will determine whether we actually understand complex interactions in the ocean in 10 years. And as a result, whether we can actually answer questions that are really important ones, like how will climate change affect the trophic cascade, that is the food web in the ocean, and impact the marine food resources that 2 billion people on the planet depend on for protein. So 2 billion people on the planet have seafood protein as their primary source of protein. How will ocean warming and heat waves affect the ocean's ability to keep on taking up 28% of the anthropogenic CO2, 93% of the heat? We really, we have ideas that are based on theory, but we're really drastically undersampling the ocean to be able to answer really important questions like that. Atmospheric rivers are phenomena in the atmosphere, but they're driven by the ocean, and their water vapor comes from the ocean, and they're the primary source of transport of water vapor from the ocean to land. And as you remember from your basic physics, water vapor is also heat because it took heat to generate the water vapor. So as these move into polar regions and then release water vapor as precipitation, they're heating polar regions. So what kind of feedback is going on there? For security forces in the face of a dense ocean network, can anyone hide in the ocean? So these are important questions for our economy, for our security, for the habitability of the planet. And they're really important for us to be able to address. And that brings us to the UN Decade of Ocean Science for Sustainable Development. So in December of 2017, the UN General Assembly agreed that the decade from 2021 to 2030 would be the UN Decade of Ocean Science for Sustainable Development. And I've been part of the planning of the decade. And when just before the beginning of the decade, the UN released a call for proposals to be multidisciplinary, multinational, multi-year programs that would operate over the decade to really transform our ability to describe the ocean, to measure it, to understand it, and to inspire action on the ocean we need for the future we want. So what kind of our future will depend greatly on the ocean continuing to take up heat, continuing to take up CO2, on the ocean continuing to provide protein for all of those people, for the ocean continuing to support ecosystems that do other things that we count on them to do, cycle carbon and so forth. And so these programs many of these programs are focused on sensing, measurement, and creating distributed sensor networks and really dense arrays of capability. Some of them are focused on adding biogeochemical measurements to that Argo system. In other words, being able to measure things like oxygen, nitrate, phosphate that the food webs depend on. Others are focused on using the new tools of biology, biomolecular measurements, and omics, genomics, transcriptomics, et cetera, and using developing sensors that would allow us to measure the distribution of these biomolecules at sea and transfer that data back. In other words, have little analytical laboratories floating around in the ocean or being directed. And of course, we'd really like those different kinds of instruments to be able to share data with each other. So if the sensors looking at the physics of the ocean see something going on, we could direct these biomolecular analytical instruments to go to that location and to see what impact the physics is having on the biology. So those are really the things that we dream about doing. And of course, we dream about being able to sit in our offices or in our laboratories on land and be able to tell the instruments at sea what to do. So those are, this is the new ocean that we dream about, and the new ocean science for sustainable development that we're trying to generate over the next decade. And all of those are really dependent and will be paced by the development of an internet of things for the ocean, so that we can add to the excitement of doing something like this in person, the ability to do it everywhere in the ocean and be able to do it remotely. So thanks very much for the opportunity to just give you a very brief idea of some of the challenges that we have and the ambitions that we have for this ocean Internet of Things.